Greetings again. So this is the second part of our week 5 lectures on video, and this time we're going to talk about performance testing. So one of the things that we need to do when we actually want to know how a given, let's say, system, whether it's a processor or a computer or some other system that's working on some work, some task, would be to characterize the kind of workload that system will be subjected to. So in the context of computers that our focus um, is located upon, we really want to think about at the maybe lowest level of detail what instructions our computers execute. So this sort of a study, statistical study, um, had been conducted in the 1970s, for example, and an instruction mix was compiled by the, I guess, the person who invented it, Gibson, and it's called Gibson Instruction Mix. And so in this mix, we take the types of instructions, we classify them into certain types, and then we write the frequencies of occurrences of these instructions as we uh, look inside the computer programs that are real programs that people actually have written. And from this analysis, we could sort of like try to optimize. Now that we know, let's say, that programs on the average have these statistics, these proportions of frequencies of, let's say, usage, then we could possibly build better, more optimal systems in this regard. So they add up to 100% here. As you can see, that load and store instructions take up the biggest chunk, and then the indexing takes the next big chunk, branching, and then floating point add and subtracts, integer add and subtracts about the same percentage. And then you have non-register type of instructions, shifts and compares and floating point multiplies, logic, floating point divide, fixed point multiply, fixed point divide even, and then total gets up to be about 100. Now, so here's an example of how to use these particular, the Gibson mix of percentages frequency-wise. So let me just fix this real quick here to take care of it. And so when I look at these classes of instructions, I'm, in this example, stating how two different processors basically execute these in the number of clock cycles that they actually consume to get these types of instructions executed. So both processors, for example, take 2 clock cycles to load or store, and indexing the same, but the branch instructions, for some reason or another, takes longer. They take longer on processor 1 than on processor 2, and floating point adds and subtracts takes also longer on processor 1 than on processor 2. So you could see how these numbers, and then in other cases, like floating point divide takes actually shorter on processor 1 than on processor 2. So now we have these numbers of clock cycles. We want to know how these two systems compare. So what we really want to do is to compute the average execution time. And in computing this average execution time, and I mentioned this in class, I think the approach that I've actually used in the notes and in the PDF files that I email you is not quite accurate, because it does use what we call the weighted average approach. But as I said in class, and in fact when I looked at the source, the original file, this change was made in the source file, that we should really use harmonic averages, because this is a rate problem where we're looking at clock frequency, or the number of clock cycles rather, divided by the number of instructions. That's what really average execution time here would be, number of clock cycles per instruction. And so that's a rate, and then because it's a rate, we really need to use harmonic averaging in the context of average service time. So therefore, when I compute these average clock cycles per instruction, terms. I'm using harmonic means, as you could sort of see how that comes about. These would be different than what I did, I guess, in the PDF version of the lecture notes, where I used weighted averages. So this is the corrected form, and I urge you to contrast this with the solution that I've given in the lecture notes, and convince yourself that this is the way it should really be done. Anyway, numerics is not as critical, but the execution time comes out to be 0.885039 nanoseconds per instruction. That is the CPI. That's not the CPI, I beg your pardon. That's the actual time based on the clock frequency of this first processor. This is really the number of clock cycles per instruction here, but this is the actual time per instruction, which then can be converted by taking this 1 over into number of millions of instructions per second. And we did that in terms of million, but this really becomes a billion, 1.1 billion instructions per second, or roughly speaking. And then we do the same computation for CPI too, same methodology. Now they're very close together, 2.478, 2.475. Now this is a slower machine. It only works with a 2.4 gigahertz clock. As a result of which, because their CPI per instruction, number of clock cycles per instruction are about the same, but one is relatively faster than the other, which this is faster than this. So the execution time comes out to be more nanoseconds per instruction, and then of course less millions of instructions per second is what happens in the second case. Now this is really not execution time 1, but it's execution time 2. So let's stand corrected in there. And so you can see that second system is inferior, and then the first system is actually better than the second one. So the machines, of course, are, as fast as they may be, they are still sort of like spending more than 2.4 clock cycles per instruction. So that's just based on instruction mixes. We can actually come up with CPI rating, and then also called MIPS rating. This is called MIPS per second, millions of instructions per second. And if they actually come up to billion, then we can call them BIPs, like billions of instructions per second. But here's 0.969 BIPs, if you want to make this in terms of billions of instructions per second. Now, the instruction mixes are one thing for performance testing. The kernels are entirely different. Kernels are basically programs. They're really workloads that are just like actual programs that people use to measure performance. So they have hundreds of instructions, if not thousands, inside them. And that's what we really use to test these computers we want to test their performance for with these. So typically what we do is we just read the number of clock cycles that has elapsed since the processor was turned on, and then divide it by the clock frequency to get the time of start. And then run the kernel, and then read the number of clock cycles that has elapsed since the processor was turned on, and then that becomes the end. And so the execution time will be the difference between the T-end and T-start times that you recorded. Of course, if the machine is running other things in the background, then there may be some impact of that on this time. So some time may be, but this nonetheless assumes a typical load on the system, and then you still run the kernels, and you can use a compiler to carry out this, and then whatever time that really is consumed by other processes to slow the execution of the kernel, you just have to make similar assumptions or similar actual conditions created. So that's how you get to compute your two systems' performance. And the execution time, of course, would be relevant here in terms of what performance we can get out of our kernel. And here's a Fibonacci kernel, which I've actually adopted from Mr. Alberto's original, basically kernel performance code. And what basically it does, it just simply starts the time, and then it calls the function called Fibonacci, and then ends the time. So between the two times we compute is the amount of time that, let's say in this example, Fibonacci 40 takes. And we repeat this, I guess, within a loop for a certain number of times. Like here we do it, I guess, 5 times, and then that will give us some average, some sense of average execution time. Now, with the computation, with the determination of the execution time, which comes out of direct measurement from our, if you like, testing process, we can gather more information. And that would be by simply looking at the assembly code, for example, that our machine executes to do the Fibonacci code. Of course, this basically overlooks the possibility that the code that we really have used may not be optimized, but that's not something that we can fault the computer with or credit it with either. And that is to say, if someone doesn't write good code, we cannot really put the blame on the computer. So effectively what we're trying to do is to remove that potential situation, that potential liability for the computer on which we execute, let's say Fibonacci. We try to look at the number of instructions executed and how quickly that happened. So that kind of isolates the problem a little bit. So what I did in this situation, I actually looked at the assembly program that I generated by using Xcode's features. That this is the compiler that I use for my Mac, and then I get a certain number of instructions, from which I was able to surmise, and there are 2 calls that are made here to the subroutine. I was able to count how many instructions that I get to execute. These are all instructions here. These are all Intel instructions. And that led me to writing a recurrence, which is basically kind of like Fibonacci, except I counted, for example, 23 instructions that would be needed to compute Gn in terms of the sum of Gn minus 1 and Gn minus 2. So that 23 came about because I started to count from top to bottom, for this function to basically execute these instructions from top to bottom would simply result in one pass of this call here. So Gn minus 1, of course, that's the call to the function itself. So whatever number of steps I've actually expanded here would have to be expanded within this and within that as well. But the 23 here just signifies how many instructions I get to do to compute Gn in terms of Gn minus 1 and Gn minus 2. Not really to compute, but this is the actual number of calls, instructions that I get to do the Fibonacci, I should say. This is the recurrence that really tells me the number of instructions, not f of n or Fibonacci n, but g of n. And g2 and g1 are the 2 terminating cases, in which situation that I only do 12 instructions. I'm looking at the conditions that actually take me out of this this function call, and that actually gives me 12. So you can really compute these numbers yourself. I'm not going to talk too much about how I get those numbers. They're not that difficult. If you look at the code, you should be able to get those. So with the constant specified, we have a recurrence, and we can actually solve this by various methods that exist out there for writing solutions for linear recurrences. But the better solution would be to run this, write a program that actually computes this, and that will be the number of instructions, let's say for 40. So if you just compute this by way of a C program, just like the Fibonacci functions itself, computation itself, then you get Gn. And so the way to do that is to substitute n equals 40 and make the computation, and that happens to be this, I guess, 3,581,695,402 instructions get to be executed. Once you know this, and you know the fact that it took, let's say, 1.35 seconds, that's what happened on my machine, we can now compute the number of instructions per second, or the bips, the billions of instructions per second statistics of this machine. And then we can also compute from that number of seconds per instruction. If you really knew the frequency of your machine, you can then go and compute the CPI, number of clock cycles per instruction, which is one of the performance metrics that people use all the time. So you can see that even at the kernel level, we could still take things back to the machine layer and figure out in these terms, like the CPI, the execution time average, all these other terms that we have used to really determine how well a computer does with those metrics. So that's just like kernels. And then you really have benchmarks. Benchmarks are like a bunch of kernels put together. So what you do is you take things, of course you can apply them to all kinds of components in the system. It doesn't have to be just the computer's processor. It could be the memory, it could be hard disk, it could be other interface boxes. You could do this. But what is critical is that you set up a loop, like in this case. Again, of course, you always mark the beginning of the time. And then you call your functions one after the other. These are basically part of your benchmark. These specify your benchmarks. Each of them is really a benchmark, if you like, but you can also view them as a kernel, so this becomes one benchmark, effectively. And then you do the execution, and then you read the time again. So the difference is basically the total execution time. What you do then, you compute what's called loop count per second. So you take the number of times you computed this, which is actually loop, that's the quantity, and divide it by TE. So as TE becomes large, your loop count becomes small. If TE becomes small, then your loop count increases. So the loop count is basically how many rounds of these calls that you're able to do. And that's kind of like the amount of work you produce, right, per unit time. And that's what this is. Like, you know, how many times you were able to go through this in this TE time. And typically, since loop is fixed, the TE will change from one machine to another, so your loop count will change, and that's how you're going to be able to get your performance. Of course, the index loop count would be the ratio of loop count to loop count reference. But these being basically throughput kind of ratios, if you like. This is like a throughput ratio. So lots of benchmarks were really incorporated into this performance testing, and I guess the most recent ones that I track would be in terms of integer and then floating point benchmarks would be CINT 2006 and CFB 2006. Like basically, spec. These are called spec benchmarks, and they really deal with a bunch of programs, and they're written down here. Compression, compiler, design, combinatorial optimization, and so on. So, and then chess. These are the ones that people use to benchmark machines. So with these benchmark figures, we could really compute our loop counts, and the loop counts will be throughputs, and then throughput ratios will give us relative performances. So when we think about execution time ratio, this is kind of like a little bit like speed up, and that's what I'm referring to here. So basically, these benchmarks produce two things. One is called throughput gain, or the rate in spec terminology, and the other one is the speed up. So speed up and rate are two metrics that are used to basically compare machines. So for a preprocessor system under test, the normalized execution time of a benchmark would be, let me just go back here, the t-test over p. That is to say, this is like when you have the test machine taking t-test amount of time. Now, of course, the normalized time would be t-test over p. and that's for a P processor system. And then the throughput gain will be P Tref divided by T test. And so you could see how this really comes about. It's really Tref divided by T test over P is what you effectively compute here. And Tref and T test are the execution times of the benchmark and the on the reference and the test machines, respectively. So you could see that because of this formula, we actually have a relationship. Let me just say this. Maybe I think I copied things over here. Maybe just take this out of here. Seems like this was a little bit of a leftover here. So now we go to the next slide. So you could just see that there is a relationship between the rate performance, which is the throughput ratio of test versus reference, and then the speed up. And so this relationship is really intentional in that you can kind of like basically get one of the performance metrics from the other. If you just compute the speed up, then you can actually multiply that by P to then compute the throughput. And that all of that comes from here. Like this is the speed up, and that's the P times the speed up that kind of gives you the throughput. Again, that of course is obtained by just simply looking at Tref over T test over P, and where T test over P is like the normalized time of the machine that is run in parallel or with P processors. And that is to say that the time is shrunk. And this is kind of like Amdahl's law without that sequential part of the computation, if you like. But since this is the actual time observed, dividing that by P is like normalizing it to per processor, and that then ultimately, when ratio to Tref, kind of gives you the rate. Whereas this is the speed up, this becomes the rate. And so that's a relationship here. Now, we could also relate to things by way of maybe Amdahl's Jane law or just Jane law itself. If you remember, we had written once the throughput of two machines, throughput gain really of two machines, test versus reference, as taking a task and then scaling it p-fold, and then dividing it by the amount of time it takes to compute it, and then ratioing that to the time, the throughput that you'll get by having, let's say, j jobs, but then taking t reference time to do it. So again, if you look at this, you all of a sudden you get this x test ref is equal to p test p times s test over reference. So this rate speed up relationship really remains dominant in the so-called spec benchmark. And all of these comments that I've actually written down here just pertain to this. So I'm going to pass this just to bring us to how to maybe take a bunch of benchmarks and then compute average speed up and average throughput gain metrics, the rate as benchmark, spec benchmark people call it. So the geometric average is something that comes to mind here, and we take these so-called two systems, the test versus the reference, and we compute speed ups, and then we multiply the speed ups, and there are m of them, and then we actually take the mth root of the product. We do this in both the speed up and the rate performance metrics. And again, because this is the kind of, I guess, average metric that works, we retain the relationship between the speed up and the rate. And so each of these would have given us basically like x of test 1 over ref 1 would have been p times this s test 1 over ref 1, and then the same way for the other terms. But all these p's multiplied m times, basically just p to the m that you get out of this, and then that kind of like comes out and then becomes a factor. And so the average rate is like p times the average speed up, which is kind of nice because it just maintains this proportionality even when you take a whole bunch of benchmarks and then put them together um, by way of these ratios. So because of the fact that when you take the geometric mean of a set of m ratios like a1 b over b1, a2, b2, and so on, and if that happens to be less than 1, then of course the geometric mean of the ratios of the numbers like b1 over a1, b2 over a2 will have to be greater than 1 because the two geometric means would multiply to 1. So that's a consistent metric, average metric, because it actually does not lead to any ratio games we talked about. That ultimately, if in fact one way of measuring the performance, let's say we measure the performance test or reference, we get the average speed up or average rate to be greater than 1, then if we just reverse the role and then look at ref over test, then we'll have to get a performance in each of these two categories that's going to be less than 1, and therefore the conclusion will be consistent. One issue that I talked about briefly in class, regarding geometric means, is that if a given system is faster, let's say, speed up wise, on so many benchmarks, but only in one, and that's by a large factor, then you can actually end up having something like in this example, a speed up that tends to 1, but that's not really fair because, like in this example, 9 out of 10 times this first system, let's say, test machine is twice as fast as the reference machine, but then in the last category, it's actually 2 over 1,024 times sort of like fast, which means like that much slower. And now all of a sudden you have actually a formula that says the speed up is equal to 1. So it's not well balanced when you have situations like this. The final thing that I want to talk about is harmonic mean. We really talked about this extensively. And we have written throughputs, and then we've written the harmonic mean of those throughputs with respect to the weights that we have. What is really left to work on, and I'm going to leave this as a homework problem, is to look at the harmonic means of ratios. This just establishes what we already know, which is to say when you take the harmonic mean, you can actually figure out that this harmonic mean is like the true average that we're supposed to take when we take all the jobs together and then divide it by the total time needed to execute the total amount of work. And then that's what this formula ultimately computes to, and that's pretty apparent to us by now. But the thing is, this is what I really want to say, that you can actually take harmonic means of ratios, and I ask a problem. I have a problem at the end of this last portion of this particular chapter, which really shows you what the formula is, and I want you to work on that. So here you have these problems to work on as part of the two lectures that I've given on during week 5, and I'm going to just send out an email to you and tell you what the deadline for this or the submission due date is, and then we can kind of work from there. So this really brings us to the end of our video lecture 5, the second part, and I'll put both these things on YouTube so that you can actually get to see them. So until next time, take care everybody, and I'll see you in class on Wednesday.